If we apply shear force up on this side, down on this side, we create shear stress, which can cause breakage of an object. And our first instinct is to think about that shear stress as being perpendicular to the length of an object. But it can also be parallel to the length of an object. Here, this object was a wheat thin. Delicious. For example, if we apply the same shear force to a deck of cards, up here, down here, we can see that that deck of cards, each card kind of slides a bit relative to the other cards, and that's because of shear stress. It turns out the parallel shear stress is equal in magnitude to the perpendicular shear stress. You can really see when I hold the cards like this, as I increase the shear stress, you get to see more of that horizontal sliding between the layers. And that horizontal sliding is due in part to horizontal shear stress.
And here is your equation for shear stress. And this is both horizontal and vertical. Because remember, the magnitude is the same for either direction. The general concept behind this equation here is that the larger the area over which the shear force is distributed, the lower the stress is going to be. But the higher the shear force, which is V, the higher the shear stress, which makes sense. Q is the first area moment. What Q means is that you only look above the middle of your beam, or in this case, let's look at a deck of cards. So this is the centroid. That line goes through our centroid. We only look at above that line to figure out our Q, or below would work too. So here's H, the height of our deck of cards when it's just laying on a table. Here's B, the width of the deck of cards. And then the long ways is going towards this end into the screen here. So we can define Q as this area above the centroid times the distance to the middle of the area above the centroid. So here's the middle of the area above the centroid. This distance here would be y bar. So to put that in terms of H and B, let's see, that area above the centroid is half of the area of the whole rectangle, which is B times H. And we multiply that by y bar, which is, when you think about it, a quarter of the value of the height. So multiply by y bar, and you end up getting for Q an expression Q equals 1/8 of BH squared. And then the value for I here, I think we've seen before, if we're working with a normal shaped rectangle, width times height cubed over 12 is the expression for that. And that's that.